This video on logarithms will jump from 13b all the way over to 13e. Alright, so you might have heard about logarithms before. Let's go through them. So we know that 2 to the power of 3 does equal 8. And what we're going to note is that there's an alternate form of writing this particular equation. So what we can say is log 2 of 8 equals 3. Okay, and what does that mean? So you'll need to be able to understand what the above statement means. So the left side can be read as a question. Okay, so that's log 2, 8 actually is a question. Now, that's the way I think about it. So I almost think about it as log 2, 8, expecting an answer. Okay, so the question is, what power would 2 be raised to, the base of the log here? What would it be raised to so that it equals 8? The answer? It's 3. So 2 would be raised to 3 to make 8. Alright, so note that ax equals y is exactly the same as log ay equals x, where a is an element of all real positives, not including 1. Okay, so the base can't be 1. Why not? Let's think about it. Log 1, I don't know, let's think about log 1, 7. This is the question. 1 raised to what power will give me 7? All right, well, the problem is that 1 raised to any power always equals 1. Okay, so 1 to the power of 2, 1 to the power of 5, 1 to the power of a half, 1 to the power of 0, 1 to the power of negative 5,000. All of them will equal 1. So this one here, log 1, 7, it can't be done. It's not possible. 1 raised to, you're not going to get 1 to become 7 by raising it to any power. So this just does not work. Right, some basic notation. This is log base 10, and it's the same as just writing the word log. So assume that if you see log, say, log 100, that means the same thing as log 10, 100. It's exactly the same thing. All right, log e. Now there's another base that we'll see more so in year 12 than year 11, but that's actually can be written as ln. Okay, so log e is the same as ln, which is referred to the natural log or the natural logarithm. Now, e is not an unknown or a variable. It's actually a known number. So e is Euler's number. Okay, and make sure you pronounce his name correctly. He's arguably the greatest mathematician that ever roamed the earth. And to hear his name referred to as Euler, yeah, we don't want to do that. Okay, so his name's Euler. All right, that's Euler's number. And we find out a bit more about it next year, but a bit like pi, it's an irrational number, roughly 2.718. And in his usual way, Eddie Wu goes through it with his 12s or 11s, I think it is, by discussing compound interest of all things. All right, so check that YouTube clip out if you want to hear more about it. All right, so evaluate each of the following. Talk to yourself. It's okay. All right, so what do I mean by talking to yourself? Well, what I do is I read this as a question. I go 2 raised to what power will give me 32? So 2 raised to what power will give me 32? I believe the answer is 5. Okay, now why do I know that? Because 2 to the 5 equals 32. Okay, so the answer to this problem here is 5. All right, this says 2 raised to what power will give me 16? The answer is 4. 4 raised to what power will give me the answer 16? The answer is 2. 3 raised to what power will give me 81? Well, 3 to the 3 is 27, 3 to the 4 is 81. Okay, so this one here, the answer is 4. 5 raised to what power will give me 125? That's 3. And 3 raised to what power will give me 27? The answer is 3. So it seems you can only find the log of positive numbers. Explain why you can't find log 4 equals negative 16. So what that means is 4 raised to what power will give me the answer negative 16. And we might remember from last year from exponential functions, if I graph y equals 4 to the x, that's what the graph looks like. It's an exponential function. Note that you're never going to be able to produce a y value of negative 16, which might be somewhere down here, y equals negative 16. And the fact of the matter is, no matter what power you try to raise 4 to, you're never going to equal negative 16. Now, many students will say, well, I think you can, right? So 4 to the negative 2 will equal negative 16. Well, actually it won't, because 4 to the negative 2 is 1 over 4 to the 2, and 4 to the 2, that's 1 over 16. And what we can clearly see is 1/16 can no way, shape or form be the same as, considered the same as negative 16. So these are not equal to each other. So you're never going to find a power to raise 4 to equal a negative 16, or a negative number for that matter. All right, so there's heaps and heaps of log laws. Well, not heaps, there's a few of them. All right, so when we're adding logarithms with the same base, what we do is we can multiply the number that's being what I call logged. Okay, so this, we've got same base logs here. So what we can do is rewrite this with m and n being multiplied together and use that same base. It's based on the index laws. Okay, so yeah, the proofs of these are in the textbook. I'm not going to do the proofs. You just need to have a look at the laws and consider them and apply them. Okay, this here, what we've got is a log base A, and these same base logs are being subtracted. What we do is we divide the powers, not divide the powers, divide the number being logged. Okay, here's a pretty cool law here that helps us a lot. So log A m to the power of p is exactly the same as p log a m. Okay, so they are exactly the same thing. So when I talk this through, I say we grab this index here, we can plonk it out the front as the coefficient. If this is true, then what I can also do is if m is being raised to the negative 1, I can grab that power and plonk it out the front. That's negative log am. Right, log a m to the n and log a m to the n are not the same. Now I'll show you the subtle difference between them. Log a, let's go m squared versus log a m squared. Now, syntactically, what this one means is if I subbed in a value for m here, like 3 or something like that, I would square it. This one over here means I sub in a value for 3 and square the result once the value is being logged. Okay, so these two things are not the same. And one final one here is this particular rule here will also get you out of a few jams. A raised to the power of log AB. So I noticed that a base is being raised to a log of the same base. What the answer will always be is just B itself. And if you think about it, here's one example of how it would be true. 5 log 5, 25. The answer is 25. Now, why is that the case? Because 5 log 5, 25. Log 5, 25 is equal to 2 equals 25. 5 squared, 25 equals 25. Okay, so that's why they are exactly the same thing. It works for every particular variation. All right. Evaluate each of the following using Rule 3. We've done these earlier. So what's Rule 3? Well, I'd be willing to bet that what we want to do is re-express this. So I'm going to write this in a different way. So instead of doing 2 to the 32, I know that the answer is 5. I'm going to write this here as log 2. Now I'm going to write 2 to the 5 like that. Now Rule 3, I'll be willing to bet, says grab this index and plonk it out the front. We've got 5 log 2, 2. Now 2 raised to what power will give me 2 as a result? The answer is 1. So log 2, 2 is in fact just 1. That's 5 times 1, which is just 5. So notice we get exactly the same answer. I think the more efficient one is the way we did it earlier, but it just shows you why Rule 3 actually works. This one here can be rewritten as log 2, 4 to the 2, which can be rewritten as log 2, 2 to the 4. And what we're going to do is grab that and bring it out the front. 4 log 2, 2. Log 2, 2 is 1. That's just 4. One final one. Log 4, 4 squared is equal to 2 log 4, 4. That's 1. The answer is just 2. All right, let's simplify some. All right, so for this problem here, what we want to do is start using some of the other log laws to simplify this down. Now, the reason I can see that we're going to be able to use some laws is I've got base 10, and base 10. And I know that there's a law that allows me to manipulate things when I've got addition and subtraction. All right, so the first thing we want to do is get rid of these coefficients here. Okay, so we need the logs to have a coefficient of 1 if we want to run these laws. So that's log 10, 3 squared plus log 10, 16, take away log 10, and that's going to be 6 on 5 all squared. All right, let's evaluate those indices. All right, now which one do we do, the subtraction or the addition? Well, you follow the order of ops. The order of ops says addition or subtraction, whichever one comes first. We're going to manipulate this one here. So we've got same base logs being added. The rule will say that you multiply. 99, 6, 9, it's 144. All right, now what we do when we subtract common base logs is we divide. And when we divide, we just use our fraction rules here, which is log 10, 144 times 25 over 36. 3672 once 4 times. Log 10, 4 times 25 is 100. 10 raised to what power will give me the answer 100? The answer is 2. So that whole thing there is a very fancy way of writing the digit 2. Okay? They're exactly the same thing. All right, let's go over here and do this one. Log 3, 4 plus log 2, and I'm going to go straight away here and go 2 to the 3, which is equal to 8. Take away log 3, 8. Now, the common mistake that students will do is they cancel out these because that's being subtracted, but you can't do that. You've got to follow the order of operations. The order of operations says you've got to do the addition first. So, I wrote the wrong base. It should be 3. All right, so we're going to go log 3, 4 times 8 is 32. Take away log 3, 8. And then we're going to go log 3. These are going to be divided according to the rule that governs subtraction between common base logs. 32 divided by 8 is equal to 4. Now that's the best we can do for that one there. We can't do any better in this scenario. Now I should sort of say why not? Well, because 3 raised to what number will give us 4? The answer is clumsy. Okay, the answer actually to that is, let's work it out. So shift 6 will give you the log template. 3, 4. There it is in standard or exact form. I'll explain why it converts it to base E. Let's get the approximation. Roughly raised to 1.26185 will give us the answer. So 3 raised to 1.261859507 ... will give us the answer. What's a better way of writing the answer? Well, it would be to leave it as its exact form, like that. All right, let's do this one. So I'm going to bring that up. Log 2, 8 to the x plus log 2, 8 to the 1 to the x. Okay, common base logs being multiplied. so being added, so what we do is we multiply. So that's log 2, 8 to the x, times 8 to the 1 take x. Okay, and that is log 2, 8 to the common base logs, or common base indices. So we add the powers, so x take x, that's going to be 8 to the 1. 2 raised to what power will give me 8? The answer is 3. So that is equal to 3. It's quite amazing. Okay, what we're going to do is solve some logs now. Okay, now 5, when 5 is raised to the power of 3, it equals this unknown number. What would the unknown number be? Well, let's write it or convert this to exponential form so we can see it. So the way it works is we loop around like this, okay? And I've heard this being referred to in other classes as sleigh, because it kind of looks like a sleigh that Santa, there's a beard, a hat, okay, is driving, okay, with a sack of presents on his back. All right, so all you do is you follow this around. Okay, so the way it works is 5 raised to the 3 will give me that unknown value. And what is 5 to the 3? It's 125 equals x, and we've solved it. How can we see for sure? Log 5, and I'm proposing that x is 125. So I think about that. 5 raised to what power will give me 125? I think the answer is 3. There it is there. So it's all syncing up nicely. Okay, let's solve this one. 5 raised to the 2 will give us this thing here. So 5 to the 2 equals 2x plus 1. So just follow it around like so. That raised to that equals that. Okay, that's 25 equals 2x plus 1. 24 equals 2x. X equals 12. Okay, and again, you can kind of check it out. Log 5, 2 times 12 is 24, 25. What does that equal? 5 to raised to what power will give me 25? The answer is 2. Okay, a little bit harder, but not really. Okay, let's do this one here. So, we're going to say that this is, the way we're going to do this one is we're going to combine these two logs by dividing. So I'm going to say that this is log 2, 2x plus 1 over x take 1 equals 4. So that divided by that. All right, now let's switch this to exponential form. So I'm just going to use that move. 2 to the 4 equals 2x plus 1 over x take 1. Now 2 to the 4 is 16. Now we're going to multiply both sides by x take 1, 16. X take 1 equals 2x plus 1. 16x take 16 equals 2x plus 1. 14x equals 17. X equals 17 on 14. There's my answer. Okay, just to go through it, your calculator will solve logs quite nicely. So let's do one on the calc. We'll do that one. Solve. Now, the log can be accessed by doing Shift and 6. Try that again, Shift and 6. We've got 2x plus 1, take away Shift and 6. Why isn't that working? Shift 6. Oh, come on. Third time lucky. Okay, 1.214, or to be exact, 17 on 14. All right, so yeah, calculator does these quite nicely. All right, let's do D. Okay, so let's combine these. So I'm going to do this one a little bit of a different way to show you another technique. Log 3, x take 1 over x plus 1. And what I'm going to do is use a technique that's very similar to equating coefficients. log 3, 3. All right, so what have I done? I've combined, ooh, that's a bit naughty. Let's go back. Okay, log 3. Now this is common common base logs being added. So I multiply. X take 1, x plus 1, all being logged, equals log 3, 3. All right, so I've used the rule there. When I add two common base logs together, I multiply what's being logged. And I've just said that this right-hand side, instead of equaling 1, I'm going to say that that equals log 3, 3. Now what I'm going to do is, because I've got log 3 and log 3 there, I can simply equate these things here. That's x take 1, x plus 1 equals 3. All right, now what does this look like? It looks like a quadratic that needs to be solved. So x squared, take x, plus x is take 1 equals 3. X squared take 4 equals 0. This is the long way of doing it, but x take 2, x plus 2 equals 0. X is equal to 2, x is equal to negative 2. All right, so are both solutions valid? Let's ask the calculator and see what the calculator says. I'm going to go a solve. Now, I've got a quick way of typing this in, so I'm just not going to use Shift 6. I'm going to type in log 3, x take 1 plus log 3 x plus 1 equals 1 for x, please. X is equal to 2. So we've ended up getting two solutions. Calculator has only accepted one. Now, what is wrong with this one? Well, once you solve the quadratic, don't forget you've got to test your solutions. So let's put 2 into this and see what happens. So when I put 2 in there, I get log 3, 1. Yep, can do that. Put 2 in there and I got log 3, 3. Can do that. If I put negative 2 in, well, what happens? Negative 2 goes in here. That's log 3, negative 3. Now, what's the problem? 3 raised to what power will give me negative 3 as an answer? Any power you feed it, it won't work. 3 to the x is always above the x-axis. It's never going to be negative, okay? So what we've got to conclude here is that x is equal to negative 2 is an out-of-domain solution, okay? So what we're going to do is look at the lowest value of x that this accepts, okay? So it's got to be above 0. So this one here is x greater than 1, and this one here is x greater than negative 1. Okay, so it's clear that the lowest value that this particular left-hand side will accept is more than negative 1. So we're going to say, but x greater than negative 1, therefore x is equal to 2 only. So this one here gets chopped out. It's a solution to this quadratic, but it's not a solution to this overall problem. Okay, and I've got to justify why I can vet out that solution. All right, let's try a couple of party tricks. Approximate, then use CAS to find solutions to the following. So here's what you should be able to do. You want to be able to work out roughly what this will be. Okay, so you've got to think 2 raised to what power will give me 6 as an answer. Well, how do I do that? So 2 to the 2 equals 4. 2 to the 3 equals 8. 6 sits in the middle of 4 and 8. So it's somewhere between 2 and 3. So I'm going to guess that the answer is roughly 2 point something. All right. This is a little bit hard. I know that 6 is in the middle, but it probably won't be in the middle. I'm going to go and guess 2.4. I don't really know with any confidence the 0.4, but I know that the first one has to be 2. All right. Now let's evaluate that. So shift and 6, log 2, 6, and 2.58, 2.6. I got 2.4. Now, I was wrong, but if you think about it, if that's a number that I have to plot on the number line and I'm trying to imagine where that is on the number line, and I said 2.4 and the actual answer is 2.6, 2.4 is a pretty good approximation of that, okay? All right, 2 raised to what power will give me 25 as an answer? Well, let's not put that down. Let's go 2 to the, all right, what's 2 to the 4? It's equal to 16. 2 to the 5, it's 32. Where does 25 sit in relation? It's 9 away from that, 7 away from that. I think it leans more to the 32 than it does to the 16. So the answer has to be between 4 and 5. So I'm going to say that the answer is roughly 4 point, and because it leans closer to the 32, I'm going to go higher and say that it's 4.7. We're working at 225. 4.6. All right, got me. I got that one wrong, but it's a pretty good approximation. Okay, this final one here is a little bit tricky. Okay, so the way I would think about this one here is that 2 raised to what power will give me 0.6 as an answer. Let's think about it. 2 to the 1 equals 2. 2 to the 0 equals 1. 2 to the negative 1 is 1 over 2 is 0.5. Now notice that 0.6 sits somewhere between 1 and 0.5. What does it lean closer to? It leans closer to 0.5, which means it leans closer to negative 1. So I suspect that this one will be roughly 0.9, okay, and negative at that. All right, let's see how I went on that one. Shift 6 to 0.6. All right, so I was off, okay, negative 0.7, I got negative 0.9. Even still, I'm not trying to make excuses. That's pretty good if you can do that, okay? So if you can actually approximate it roughly to within 2 digits of the decimal, 3 digits of the decimal, I reckon you're going all right. Okay, so there's the questions. Use those log laws and see how you go.